So continuing from where we left off, let's move on to number 5, which is explain what it means to bisect a segment. Why is it impossible to bisect a line? So I found the perfect example of a segment, right? Segment is essentially just a line with two clear endpoints. So now what does it mean to bisect? It simply means to go ahead, find the midpoint, right? And divide our segment into two equal pieces, right? So to bisect a segment means to divide a segment into two equal pieces. Voila. Then now let's take a look at why it's impossible to bisect a line. So I kind of have an example of a line here. As we know, it never ends, right? It goes on and on and on and on. So think about it. Why can't we bisect a line? Well, simply because we don't know where the midpoint is, right? Because it extends infinitely in either directions, correct? So because our line never ends, therefore it doesn't have endpoints, and because of that, we don't know where the midpoint is, and therefore we cannot bisect our line. All right, so now speaking of bisection, we have segment AB. So all right, so for number 6, AB bisects CD at point M. So I have a segment CD, and it gets bisected at point M by AB, right? And AB doesn't actually have to be perpendicular, correct? We just need to make sure that the point of intersection is our midpoint, and it is M. Now, we know that AB equals 4 times CM. So if we have CM over here, segment CM, we know that the length of CM would be congruent to the length of segment MD. And if you go ahead, since AB is equal to 4 times segment CM, I can go ahead, divide up my segment AB into 4 congruent parts, and it's going to be the same distance, right? So therefore, when we're describing the relationships between AM and CD, guess what? AM is congruent to CD. Voila. There you go. AM is congruent to CD. As you can see, AM has 2 equal segments, and as CM plus MD. So next is fairly easy. We have an acute angle over here, and our acute angle is smaller than 90, so I went ahead and drew it like so. Our obtuse angle is bigger than 90 degrees, so there it goes. But also, in case you forget, our obtuse angle has to be bigger than 90 but smaller than 180, right? And then we have our right angle, which is literally 90 degrees. So our right angle is formed with 2 perpendicular lines. And then our straight angle, which is just 180 degrees. All right, for next question, it says to sketch an example of adjacent angles. And we know that adjacent means literally right next to each other. So I went ahead and sketched angle A and angle B that are right next to each other. And they have to be complementary. So that means when 2 angles are added together, their sum turns out to be 90 degrees, right? So I went ahead and put that. Measurement of angle A plus measurement of angle B equals 90. Now, the question is, are all complementary angles adjacent? And now, complementary angles do not always have to be adjacent. So let's go ahead and draw an example of non-adjacent complementary angles. You see, I went ahead, took A, maybe turned it around a little bit, put it right there, and then B stays the same. They're no longer adjacent, right? But still, their sum comes out to be 90 degrees. So yes, they are still complementary angles. However, they're no longer sitting right next to each other, so therefore they're not adjacent. Okay, so not all complementary angles have to be adjacent. This time around, I have two angles, angle D and angle E. They form 180 degrees. So when they get together, they form one straight line. So therefore, this would be a linear pair, correct? Now, in order for us to have linear pair, we must make sure that they are adjacent because we literally need to have two angles come together to form one straight line. But if I go ahead, which means since their sum turns out to be 180, they're also supplementary, right? But what if I go ahead, take D, let D stay where it is, but I take E and then I rotate it like this. So I have an angle D and I have an angle E. They're no longer, when we put them together, they don't necessarily put straight line, right? Because they're distance apart. However, when we go ahead and measurements of D and measurements of E, they still turn out to be 180 degrees. So yes, they're still supplementary, but they're no longer a linear pair. Okay, so when they ask you, are all supplementary angle linear pairs? Not all supplementary angles are linear pairs. Only adjacent. Only adjacent supplementary angles are linear pair. Okay? Alrighty. Next is tell whether the statement is always, sometimes, or never true. And we're going to explain our reasoning. An obtuse angle has a complement. An obtuse angle. So let's think about that. Obtuse angle, that's a fat angle, right? I have an obtuse angle. This angle is bigger than 90 degrees. So now it's acute. This is an obtuse angle, right? Obtuse angle has a complement. And remember, complementary angles are when two angles sum up to be 90 degrees. But our obtuse angle is already over 90 degrees, correct? So we cannot have any other buddy that could form 90 degrees with. So therefore, it's never true. Straight angle, we have a straight angle and has a complement. Again, complement. When we are having complementary angles, the sum of all the angles have to be 90 degrees. But a straight line, that's 180 degrees. That's way over 90 degrees, right? So it is never true. C, an angle has a supplement. An angle, any angle, could have a supplement, right? So sometimes it's true. Again, let's say if we're looking at a linear angle, like a straight angle, can it have a supplement? No, right? Because it's already 180. But any of the angles in between 0 and 180 could have a supplement. So therefore, it is sometimes true. D, the complement of an acute angle is an acute angle. So let's go ahead and think about what a definition of an acute angle is. Acute angle is an angle that's smaller, bigger than 0, but smaller than 90, right? I have two angles over here. I have an angle A, and then I have an angle B. Angle B. Now, when I put these two angles together, these are both acute angles, right? And then if I go ahead, add them together, what ends up happening is they come to make 90 degrees, roughly. So think about it. For all complement of an acute angle, so complement of an acute angle, because complementary angles again mean when the sum of angles turned out to be 90 degrees, right? So complement to an angle, acute angle A, should be another acute angle, right? Obtuse wouldn't make sense because that's going way over 90 degrees. So that would be always. So the complement of an acute angle is always another acute angle. E, the supplement of an acute angle is an obtuse angle. So this time around, let's say we have acute angle A, and now we're looking at supplement. So therefore, if I go ahead, put together B again, another acute angle, that's not supplementary, right? Because we want our supplementary to be 180. So all the angles added up together should be 180. So therefore, it can't be another acute angle. So that means I would have to come up with like multiple angles, right? If I were to find supplementary angle to this acute angle, that angle would have to be going over 90 degrees. So therefore, it would have to be obtuse. So the supplementary of an acute angle is always an obtuse angle. All right, to better demonstrate the next question, which is tying a string tightly around the polygon. And right now I have a convex polygon. I have a convex, not convex, of course. Yes, I have a convex pentagon over here. Now I pretended like I could tie a string very tightly around my pentagon, and yes, this seems like it would be the length of the string, right? So the total length of the string will be the perimeter. Perimeter is a distance around the polygon, 둘레 in Korean. So yes, it would be the perimeter. That's pretty straightforward. Now, how about if we have a concave? If my polygon is no longer convex but a concave, so I have one of the interior angles be bigger than 90 degrees over here, guess what happens? If I wrap it around tightly, I mean, yes, I can go ahead, try to insert this like that, but that would change the entire length of the string, right? So actually, the perimeter of the polygon would be bigger than the total length of the string because of this angle that is this obtuse angle that happens to be one of the interior angles of the polygon. And next, we have to draw a figure that fits the description, a triangle that is not regular. So we have to first think about what makes a triangle regular. In order for us to have a regular triangle, we need to make sure that all the angles are congruent and all the sides are also congruent, right? So when all three sides are congruent, we call that equilateral. And when all three angles are congruent, we call that equiangular. What I have over here is clearly not an equilateral nor an equiangular triangle. So therefore, this is not a regular triangle, right? These two angles may be the same, they may be congruent, but this angle, the third angle, is different from these two. And remember, we need to make sure all angles and sides are congruent in order for us to have a regular polygon. So this would be a good example of a triangle that is not regular. Next, we have a concave quadrilateral. So if we want to have a concave, first of all, this is a quadrilateral. Quadrilateral just means it has four sides, right? This is a quadrilateral, and this happens to be a regular quadrilateral because all these four sides are equal in length and all these four angles are equal in their measurement. So this is equiangular, equilateral, square, or quadrilateral. And this also happens to be a convex quadrilateral. Why? Because each one of the interior means inside, right? Interior angles is 90 degrees or less. Now, let's go ahead and change that into concave. So that means it still needs to have four sides, and there you go. So it has 1, 2, 3, 4. 4 sides. There you go. And they don't have to be regular. They don't have to be equilateral. They don't have to be equiangular. They just have to be quadrilateral. So here's a convex quadrilateral. Like I'm doing a YouTube haul. Perfect. Next is a pentagon that is equilateral but not equiangular. So pentagon requires 5 sides and it is equilateral. So equal in length. More or less, maybe. But not equiangular. We just have to make sure, I know it's hard to tell, but we just have to make sure that we show them that this, each one of the sides is equal. Like this. Yeah? That means this side is equal to this side, equal to this side, this side, this side. So therefore we have a equilateral but not equiangular pentagon. An octagon is polygon with 8 sides, and they have to be equiangular but not equilateral. All right, so for this, you just have to make sure we have polygon with 8 sides. And since they don't have to be equilateral, forget about, showing that the sides are congruent, but our angles have to be congruent. So here it goes. That's how I did. And for the next question, if we have a segment AB, points A and B are literally just endpoints of segment AB, right?